Stereoisomerism. Isomerism is organic compounds that have the same molecular formula but different molecular structure. There are two types of isomerism: structural or constitutional isomerism and stereoisomerism. Structural or constitutional isomerism has different in connectivity, but stereoisomerism has same connectivity but different arrangement in space. There are three types of structural or constitutional isomerism. The first one is chain isomerism, second one is positional isomerism, and the third is functional group isomerism. Chain isomerism differ in the structure of carbon chain. For example, the straight carbon chain here, C bonded to another C bonded to the third carbon bonded to the fourth carbon. So straight chain here, 4 carbons in total, and we call it butane because it has class of compound alkene. So 4 carbon butane. And this one is different isomer. This is chain isomer with 2-methyl propane. They have the same molecular formula but different in the structure. Okay, different in molecular structure, same molecular formula, different molecular structure. So again, structural isomer different in connectivity. So they have the molecular formula of C4H10. In here, C4H10 as well, but different connectivity. So this 4 carbon has 3 hydrogen. This one has 3 hydrogen attached to this carbon. This one 2 hydrogen, 2 hydrogen, 3 hydrogen. But for this one, the first carbon here, 3 hydrogen attached. Second carbon here, 2 carbon on the left and the right and 1 carbon on the above. So 3 carbon attached to this carbon. This is what it means by different in connectivity. Chain isomerism, they have different carbon chain. How to identify the carbon chain? So you look at the longest carbon chain. This one, it has the longest carbon chain, 4 carbon. And this one, longest carbon chain, 3 carbon. If you count from the left, 1, 2, 3, from the right, 1, 2, 3, and from the above, 1, 2, 3. 1, 2, 3 means it has the longest carbon chain, 3. So 3 carbon chain, here 4 carbon chain, but they have the same molecular formula, C4H10. This is chain isomerism. Second one is positional isomerism. Same carbon skeleton but differ in the position of functional group. Here, if you look at chain isomer, they have different carbon skeleton or different carbon chain. This one 4 carbon chain, this one longest carbon chain 3. But in positional isomerism, they need to have same carbon chain or same carbon skeleton. The difference is the position of the functional group. Positional isomerism must have same functional group. They must have same functional group. The difference is the position of that functional group. This one, put 2-in or 2-butene. Here, the functional group carbon-carbon double bond. This one, put 1-in or 1-butene. The functional group is carbon-carbon double bond. So for you to say they are both positional isomerism, they need to have the same functional group. The difference is the position of that functional group. Here, the carbon-carbon double bond is at the second carbon. But here, the carbon-carbon double bond is at the first carbon. You start counting the number of carbon at the functional group or nearest to the functional group. Okay, you start counting. So this is the first carbon because the functional group is at this carbon, not this one. This one is not the first carbon. We start counting at the nearest functional group. So these two, you call it positional isomerism. Next one is functional group isomerism. They have same molecular formula but different functional group. So here, functional group carbon-carbon double bond. Alkene, carbon-carbon double bond, class of compound alkene, but 2 in. And this one, cyclobutane. Cyclobutane, class of compound alkane, no functional group. Class of compound alkane, no functional group. So these two are functional group isomerism. Different functional group. Positional isomerism, same functional group, the difference is just the position. Chain isomerism, they need to have different carbon chain. This one 4 carbon, this one 3 carbon, longest carbon. Next, functional group isomerism, it's a between alcohol ether, because you have the same general formula, CnH2n plus 2O. This is the general formula for alcohol, and ether also have the same general formula. So alcohol and ether can have the functional group isomerism. Alcohol and ether, aldehyde and ketone, alkene and cycloalkane, carboxylic acid and ester, they can have functional group isomerism. Same molecular formula but different functional group. These are the general formula for them. Stereoisomerism, the second type, chemical compounds which have their atoms connected in same order but differ in arrangement in space. Two types of stereoisomerism: optical isomerism or enantiomer. Second, cis-trans isomerism or diastereoisomer. Optical isomerism or enantiomer involves carbon that has chirality center. Chirality center means carbon that have different atoms or groups of atoms attached to it. That is carbon chiral carbon. The molecule and its mirror image or non-superimposable compounds are able to rotate the plane polarized light. So I'm going to explain in detail on this on the next slide. Let's look at the second type of stereoisomerism, cis-trans isomerism. The molecule are not mirror image, so different from this one. Non-superimposable of each other. Free rotation is prevented by the presence of C double bond C or cyclic structure. Okay, let's look at the enantiomer or optical isomer first. Optical isomer, enantiomer, same thing, same definition. So enantiomer, the molecule and its mirror image are non-superimposable. Occur only with compounds whose molecules are chiral. Chiral molecule means a molecule which has a carbon attached to 4 different atoms or groups of atoms. For example, here compound A, the black is carbon. So this carbon attached to 4 different atoms, Br, Cl, HF. So you call this carbon as chiral carbon. And its mirror image is compound B, another compound that has mirror image as compound A. So mirror images are non-superimposable chiral molecules. You call the compound A and compound B as a pair of enantiomers. So this is stereoisomerism. Stereoisomerism for enantiomer. Stereoisomerism enantiomer. It has carbon that attached to 4 different atoms and it has mirror image. You call them a pair of enantiomers. So this, if you have to draw the enantiomer, you need to draw in 3D representation. Make sure you draw the mirror plane in the middle. Compound A, compound B. Make sure you have to draw distorted mirror image. And the carbon atom. Then you start with the solid line two solid line, 1, 2 solid line. The bond lies in the plane, and then one wedge line bond in the front, and this one wedge dashed bond behind. This means bond behind. And the compound B, another pair, you have to draw like you putting a mirror in front of this compound. Then you have to draw exactly how you put the mirror image is. So if this like green atom at the back, so the compound B green atom has to be at the back. This blue at the front, this blue at the front, and the red atom on the top, the black atom here at the front, these two in front of mirror plane. Next, optical activity. So we are going to describe on the chiral compound or chiral carbon. Optical activity is the ability of a chiral compound to rotate the plane polarized light. So if that compound has chiral carbon, you call it chiral compound. Chiral compound has the ability to rotate the plane polarized light. Chiral compound rotates the plane polarized light, thus chiral molecule is optically active. This is the reason why you call it optically active, because it can rotate the plane polarized light. If the compound has no chiral carbon, it cannot rotate the plane polarized light. It is not optically active. The isomer, which rotates the plane of polarization to the right, if it rotates to the right, you call it as dextrorotary isomer, D or plus symbol isomer, if it rotates to the right or if it rotates clockwise. If the isomer rotates the plane polarization to the left or anti-clockwise, is levorotatory isomer, symbol L, or negative isomer, the negative sign isomer. Polarimeter. The compound's optical activity property is measured by polarimeter. Scientific measurement used to measure the angle of rotation caused by passing the polarized light through an optically active substance. Means you put the compound that has chiral carbon and the polarimeter, and this instrument will be able to rotate if it consists of the compound with chiral carbon. So the main parts are light source, polarizer, sample tube, analyzer, scale for measuring degrees of rotation. So this is a light. Unpolarized light oscillates in all planes. And then this is polarizing filter. Plane polarized light oscillates in only one plane, and this is the sample tube with solution of optically active substance. Means you put the compound that has chiral carbon, chiral compound, in the sample tube. If it has chiral compound or if it has chiral carbon, the polarized light can be rotated and will be analyzed by the analyzer. The angle can be analyzed by the analyzer. So the plane of polarized light has been rotated if you have chiral compound in the sample tube. If non-chiral compound, if the compound has no chiral carbon, the plane of polarized light has not been rotated, so it's not changed. So this is the example of chiral compound. It has chiral carbon. This is lactic acid chiral compound, and it is optically active. So we call it chiral carbon because it has attached to 4 different atoms or group of atoms. So this carbon attached to COOH, and it attached to OH, this one attached to H, and then another one is CH3. And this is how you need to draw the optically active, enantiomer of lactic acid. So first draw one compound of lactic acid, another compound, put the mirror plane in the middle, and you have to draw another one exactly like you put the mirror in front. So this one anti-clockwise, L, symbol L, lactic acid. This one clockwise rotate, so D, lactic acid, or positive. This one negative. So L-lactic acid and D-lactic acid are a pair of optical isomers, or you call them enantiomers. This one is the second type of stereoisomerism, Cis-trans Isomerism or Diastereoisomerism. The molecules are not mirror images and non-superimposable of each other. There must be two different atoms or groups of atoms on each doubly bonded carbon atom. Means this carbon here must attach to two different atoms or group of atoms. So this carbon attached to CH3, this carbon attached to hydrogen. And if you look at this carbon also attached to two different atoms or group of atoms. So this one, this carbon attached to CH3, this carbon attached to H. This carbon attached to CH3 and H, this carbon attached to H and CH3. So the carbon must attach to two different atoms or group of atoms. Then you can identify whether it is cis-trans isomerism or not. And then for cis-isomerism, the atoms or group of atoms that attach to the carbon, they are on the same side, CH3 on the top. For trans isomerism, the group of atoms are at different sides. Look at the atoms or group of atoms, they must be on different sides. So here CH3 on top, another one CH3 at the bottom. So if they are at different sides, it is trans isomerism. If it's on the same side, it is cis isomerism. Okay, cis isomer, trans isomer. For this is for cyclic structure. Can look at on top and at the bottom. For carbon-carbon double bond, okay, carbon-carbon double bond, look at the carbon attached to two different atoms. So ClH, this carbon attached to two different atoms, one Br, one H. And then they are halogens and these two are on the same side. So you call this as cis isomer. This halogen on different side, Cl, one on top, one at the bottom here. So this is trans isomer. So these two pairs, you call them as cis-trans isomerism or diastereoisomer. Here cis isomer again, two atoms or group of atoms which attach to different carbon on the same side. More examples, so this CH3 on the same side. So here on the same side, CH3, CH2, CH3, so these two on the same side. Or if you're confused, look at the hydrogen. The two hydrogen are the same and they are on the same side. So here on the same side, cis isomer, CH2, CH3, CH2, CH3 on the same side. So this is cis isomer. Trans isomer at different side, at the opposite side. CH2, CH3 on top, CH2, CH3 at the bottom. Here one CH3 at the top, one CH3 at the bottom. Cl halogen on top, halogen at the bottom. So they have been at the opposite side, that is trans isomer.